Hi everyone. Today we'll talk about momentum and Newton's third law and use those to say a few things about gravitational assists. Momentum is mass times velocity, so its units are the units of mass, kilograms, times the units of velocity, meters per second. Therefore, its units are kilogram meters per second. Knowing this and knowing that momentum is conserved enables us to make some calculations about situations. We'll use air hockey pucks because they don't have friction, complicating things. And we'll say we have a 2 kilogram puck moving to the right at 2 meters per second, colliding with a smaller 1 kilogram puck, also moving to the right at 1 meter per second. We use arrows to represent momentum. We'll take to the right to be the positive direction. So we'll say that our 2 kilogram puck moving to the right at 2 meters per second is represented by this longer arrow, which is meant to be 4 times as long as the shorter arrow. The length of the arrow denotes the magnitude of the quantity in question. And we know the momentum of the 2 pucks after they collide because we can figure out what it is before they collide just by adding them up. So since we add arrows tip to tail and we add quantities just by normal addition, we know the momentum before the collision is 5 kilogram meter per second. That must be the momentum after the collision as well. And that means that if we know what one of the pucks is doing, we automatically know what the other one's doing. For example, if the big one starts moving to the left in the negative direction at 0.5 meter per second, then the little one is going to have to acquire a momentum to compensate for that, so that the sum of the 2 momentum must still be 5 kilogram meters per second when we add the arrows tip to tail or when we add the quantities. So since we know the little one has a mass of 1 kilogram, we can immediately say it must be moving at 6 meters per second, because that's the speed that will make my momentum after the collision equal to the momentum before the collision. We can figure this out if they're stuck together after the collision, because we know the mass of the ensemble. It's the sum of the masses of the 2 pucks. 2 kilograms plus 1 kilogram, so that's a 3 kilogram ensemble, and it's got to be moving in some way such that the momentum of that 3 kilogram thing is 5 kilogram meter per second. So in other words, since we know that, and we know that momentum is mass times velocity, we just have to say 3 kilograms times something gives us 5 kilogram meter per second. That something must be 5/3 meters per second. And we can calculate it for a breakaway. So what if our ensemble is moving together at 1 meter per second and I eject the smaller one to the left, because left is our negative direction, at 1 meter per second. So then what happens to the bigger puck? Well, I still know that if my total momentum before the collision is 3 kilogram meters per second, as it is, given the circumstances of this problem, then it still has to be that afterwards. So if the smaller one's going to be going to the left with magnitude 1, the bigger one had better be going to the right with magnitude 4. And so then, because it's 2 kilograms, I can solve for its velocity, and I get that the velocity of that larger puck must be 2 meters per second, just to make it add up. So that's a review of conservation of momentum and some of the great things we can do with it in one dimension. We could do it with different masses, though. For example, here's a 1 kilogram ball, and it's going to hit a slightly bigger ball. And by slightly bigger, I mean 10 to the 24th times bigger. And we're going to say the big ball is initially at rest, so that the total momentum of the system pre-collision is 1 kilogram meter per second. After the collision, it still has to be 1 kilogram meter per second, even if that little ball bounces off the big one and starts going in the other direction with the same speed that it had when it hit the big ball initially. Okay, so the total momentum, which has to be equal to 1 kilogram meter per second, is minus 1 kilogram meter per second plus whatever the momentum of the big ball is. And you can see where this is going. The big ball has to compensate for the little ball's change in momentum, so its total momentum must be 2 kilogram meters per second, bigger than the momentum of the little ball. But this doesn't mean the big ball moves more. It means it has a bigger momentum. And that distinction becomes important when we realize what the speed of the big ball is. It's incredibly tiny because its mass is so much bigger than the little ball. If you solve it, if you say 2 kilogram meters per second and you set that equal to mass times velocity, you're going to get that v is 2 times 10 to the minus 24th meters per second, which is like the diameter of a proton per millennium or something far, far too small for anyone to be able to measure. But this is the situation when we have very different masses. So this is a prelude to Newton's third law, because often in space we find ourselves with very different masses, and Newton's third law is a statement of the conservation of momentum. Newton's third law says that the force of object 1 on object 2 is equal and opposite to the force of object 2 back on object 1. And I'll express that in terms of masses and velocities. So mass times change in velocity per change in time. What is that? Change in velocity per change in time. That's the acceleration. So mass times acceleration, we know that's the force for object A, and we'll say is equal and opposite to the mass of object B times B's change in velocity per change in time. What's the change in time? Well, it's the time that the two objects are interacting, the time when they're in contact for collisions, or just their interaction time for more generally. But that's the same, because when object A is interacting with object B is interacting with object A. So delta T contact is the same for both sides. That means that the m mass of A times its change in velocity is equal to and opposite to mass of B times its change in velocity, which is the conservation of momentum. So Newton's third law and the conservation of momentum are the same thing. So the Earth and the Moon are one of these examples with very different masses. The Earth's much larger mass causes its velocity to change less than the Moon's when the two of them interact. So we all know that the Moon orbits the Earth. The mass of the Earth causes its gravity to cause the Moon to change its path drastically, right? It's orbiting. But we don't often realize that the force of the Moon back on the Earth is equal and opposite. So the Earth is actually orbiting too. Its orbit is much smaller, though, due to its much larger mass. In fact, it's completely within the sphere of the Earth that little wobble happens. So the difference in masses makes a big difference in this problem. But what does it mean for two objects to be in contact anyway? And do they have to be touching to be in contact? Maybe not. Maybe like the Moon and the Earth, they can be in contact gravitationally. Or like these two trains, they can affect each other. You could have, if you had similar poles to this magnet and this magnet, then when you bring them together, one will jump away from the first one even before they start touching, just because of that magnetic interaction. So the interaction doesn't have to involve an actual collision. What if we had a spacecraft get close enough to a planet that it starts being affected by the gravity, but doesn't quite go into orbit? Well, then we're going to have the spacecraft accelerating due to the gravitational force of the planet, and the planet accelerating due to the gravitational force of the spacecraft. Those forces have to be equal and opposite by Newton's third law, the forces have to be equal and opposite, but their effect is different because of the different masses of these two objects. In this case, the spacecraft's much smaller mass causes its motion to be affected much more than the motion of the larger planet with which it interacts. This is what's known as a gravitational assist. And we use these gravitational assists to get around the solar system and maybe eventually to get around much more distant destinations. So imagine this scenario. You have a train coming at you and a person throws a ball at the train and the ball bounces off the train. You get some surprising results. The ball appears to pick up some of the train's velocity. And this again gets traced back to the fact that the ball's mass is so very much lower than the train's. Here's a pixelated comic of the situation. We have the Jupiter Express, named because we often use Jupiter for gravitational slingshots. And the ball is going to be our spacecraft. The ball is meant to be coming into Jupiter at 30 miles per hour. So sorry if that's hard to read. The Jupiter Express is moving, however, at 50 miles per hour. I find it easiest to picture myself on that train. I'm in the driver's seat of that train. I'm in the reference frame of that train. In your own reference frame, you're always at rest because you can't tell, according to the train, the other objects are coming toward it. It's not moving, but everything else is moving toward it. So I'm on the train. I'm at rest in my own reference frame, and I see that ball coming at me at 80 miles per hour, right? Because that's that ball is 30 miles per hour that way, the train's going 50 miles per hour the other way. So I'll see the ball coming at me at 80 miles per hour. Sorry for the non-metric units in this example. And then it's going to bounce off the train in what's called an elastic collision, so that its speed leaving the train is the same as the speed with which it came into the train. But from my reference frame in the driver's seat, that's going to be 80 miles per hour with respect to the train in the other direction. That is the same as 130 miles per hour with respect to the ground. So switching around the reference frames, which we'll be doing more and more as the course goes on, helps you to decipher this sort of problem with a gravitational assist. This is also called a gravitational slingshot. We appear to gain speed from the planet by picking up some of the planet's momentum as we go around it. Do we get it for free? Well, no, the planet's momentum changes too as a result of this interaction. It just changes much, much less because of its much larger mass. And NASA has used this. This is a picture of Juno orbiting Jupiter. So that's one example of how we use a gravitational assist to get places in the solar system.